Thanks for watching. I will be talking about near-optimal erasure list-decodable codes. And this is joint work with Avi Ben-Roya and Amnon Tashma, both from Tel Aviv University.
Okay, so let's get right to defining our main object, which is erasure list-decodable codes. So in erasure codes, we wish to recover a message corrupted with adversarial erasures, meaning some of the bits are masked as erased. And when the fraction of erasures is too high and we cannot hope for unique decoding, we can resort to list decoding. So we say that a code C that maps messages of length n to code words of length n prime is 1 minus epsilon comma L erasure list decodable if, given a code word, where all but the epsilon fraction of its coordinates were adversarially erased, so we replace them with question marks, there exists a list of size at most L that contains the original code word. Okay, hopefully a short list. So here is our initial code word. So list decoding is highly motivated, as most of you probably know. Now let's see what are the parameters that we can hope for. So we work over the binary field in the erasures model. Now this is in contrast to the errors model, in which we allow not erasures, but errors, meaning that we allow up to half minus epsilon fraction bit flips in unknown locations. And as always, in coding theory, we have two key parameters, which are the code's rate, n over n bar, and we want it to be as high as possible because this means less redundancy, and the list size, which we obviously want it to be as small as possible. Okay, so what about bounds on the rate? So the rate can be as large as epsilon, and recall that epsilon is the fraction of coordinates we keep. And we can compare it to the errors model, where there epsilon squared is necessary for a code of distance half minus epsilon. And it makes sense to consider 1 minus epsilon in the erasures model, versus half minus epsilon in the errors model. What about the list size? So quite surprisingly, the list size can be as tiny as log 1 over epsilon. Comparing with the errors model, where there poly 1 over epsilon is necessary. I'll just mention that for linear codes, the list size is at least 1 over epsilon. We start by noting that any binary code of distance half minus epsilon can handle 1 minus 2 epsilon erasures with polynomial list size. So there is a drawback. We have upper bounds. If we just consider codes with high distance, we cannot break the rate epsilon square bound this way. Okay, for example, due to the LP bound. So in terms of explicit dedicated constructions, there are not a lot, especially for binary codes. So before our work, the best explicit code is actually a code close to the GV bound. Now, for large epsilons, Guruswamy and Indik managed to get logarithmic list size, but the rate is still not quite what we hope for. Our result is an explicit one in the small epsilon regime and gets us rate, which is epsilon to the 1 plus gamma for any constant gamma, and list size, which is polynomial in log 1 over epsilon, and the degree of the polynomial depends on gamma. So in the small epsilon regime, we break the epsilon squared barrier and manage to do so with nearly optimal parameters. So for every constant gamma and a small enough epsilon, there exists an explicit binary erasure list-decodable code with rate, as I mentioned, epsilon to the 1 plus gamma, and list size polylog 1 over epsilon. Okay, so how do we do that? First, by noticing that two primitives in pseudo-randomness are in fact equivalent to Erasure List-Decodable codes. And these are Ramsey graphs and strong one-bit dispersers. Now, two of the implications, as you see, were already observed before, and we in fact complete the picture, okay, and show that these three are equivalent. So we go through the following graph. We first construct a Ramsey graph, show that it implies the strong one-bit disperser we want, and then using the implication by Guru Swami, construct our Erasure List-Decodable code. And now let's start by defining strong one-bit dispersers. Okay, so a one-bit strong disperser is a function taking two inputs, one of length n, and the other of length d, which we call the seed, and map it to a single bit, such that for every subset x of size at least capital K, so we have a large enough subset on the left, for all but epsilon fraction of the seeds, this xy is the entire codomain. So it's 0 and 1. Another way to say that for every good y, there exists a pair of x's, x1, x2, such that one of them maps with that y to 0 and the other maps to 1. Okay, and just emphasize that the set of good seeds is not in any way universal, but depend on the set X itself. Okay, so every large enough set induces a set of good seeds and bad seeds. Now, I also want to define dispersers in terms of random variables. And for that, we need to define the notion of a weak source. Okay, so we say that X is an nk source. If X is a random variable, distributed over 0, 1 to the n, and has mean entropy at least k, meaning that for every X, the probability to see X is not too large. It's at most to the minus k. Okay, so here you have an example for a distribution with mean entropy k. Alternatively, we can consider flat sources only and treat X as just a subset of 0, 1 to the n of cardinality at least to the decay, which we denote by capital K. Okay, so here is a flat source. And in the language of random variables, a one-bit strong disperser is a function such that for every nk source X, for all but epsilon fraction of the seeds Y, we have that the support of the random variable disp xy equals 0, 1. Okay, so X may have bad seeds. For example, this set is a set for which y bad is bad because it maps the entire set, the entire support of the random variable to 1. And this is a good seed. So just to complete the picture, when we allow disp to output m bits, the requirement is that on average, over the fixing of the seed, the cardinality of the support of this distribution is at least 1 minus epsilon times 2 to the m. For a non-strong disperser, we allow to waste the seed and only require that the cardinality of the support of disp xy, when we enumerate over all y's, is at least 1 minus epsilon times 2 to the m. And there, in fact, constructions are easier. I'll just mention that dispersers are an important tool in de-randomization, not necessarily the strong variant. It allows randomness-efficient error reduction of one-sided error randomized algorithms, and is used as an ingredient in various pseudorandomness primitives such as PRGs, heating set generators, and a few others. For those of you who are familiar with seeded extractors, let's see how the two objects compare. Now, in a seeded disperser, we are interested in covering, meaning up to some error epsilon of elements that we completely miss, we cover all the domain, all the codomain, right? But if we're not only interested in covering, but we also want to cover uniformly, that stronger object is what some of you know as a seeded extractor. Okay, so there's a disperser, which only covers most of the codomain, and an extractor does it up to some error uniformly. Okay, so let's see the bounds on one-bit strong disperser. And not surprisingly, they will be pretty similar to what we saw a few minutes ago. So we have two key parameters: the disperser seed length, D, and the entropy requirement, K, or how small can the set X on the left-hand side be. And we want both to be as small as possible as functions of n and epsilon. Okay, what can we expect? So for the seed length, non-explicitly, and also it's in fact a lower bound, the seed length should be log n plus log 1 over epsilon. In terms of the entropy requirement, it can be as tiny as log 1 over epsilon. That is, in terms of set sizes, which are 2 to the entropy, a disperser works for extremely small sets of size O of log 1 over epsilon. And now let's see how strong 1-bit dispersers indeed give us what we want: erasure list decodable codes. And the statement is as follows. If we have a disperser with error epsilon and entropy requirement K, we can explicitly construct a code mapping messages of length n to code word of length capital D, which is 2 to the D, that is erasure list decodable from 1 minus 2 epsilon erasures, with list size L, which is 2 to the K, and rate, which is n over D. And if you look at that, this implication, you'll see that taking an optimal disperser with D, which is log n plus log 1 over epsilon, and K, which is log 1 over epsilon, we get an optimal erasure list decodable code with rate epsilon and list size log 1 over epsilon. Okay, so this implication preserves optimality. And what's the construction giving a disperser? How do we construct C? It's actually straightforward. Given X, a message in 0, 1 to the N, we encode X by applying the disperser on all possible seeds. So you can see that the parameters fit. Now we won't go over the proof here, but it is pretty simple. So here's our result in the terminology of dispersers. In the small epsilon regime, we construct near optimal strong 1-bit dispersers. For every constant gamma and small enough epsilon, there exists an explicit dispersers with seed length D, which is 1 plus gamma log 1 over epsilon, and the entropy is O of log 1 over epsilon, where the constant here depends on gamma. And this is the first construction to outperform optimal seeded extractors, because there, the seed length must be at least 2 times log 1 over epsilon. And we handle the small error regime, but of course the regime where epsilon approaches 1 is also very interested, especially in the coding theory perspective. Okay, great. So how to construct 1-bit strong dispersers? What we need is all but epsilon fraction of the seeds to cover 0, 1. But we don't want to do it uniformly because we know seeded extractor cannot achieve the parameters we are after. Say, typically, the situation we want is that for a typical seed, this xy is epsilon 0 close to uniform, for epsilon 0, which is much greater than epsilon. For example, take epsilon 0 to be a quarter or anything non-trivial. Meaning that a very large fraction of the seeds y are good, 1 minus epsilon of them, but each good seed is not that good. Okay, this is represented by this epsilon 0. And now a new player comes into the picture that will help us make this distinction between both sources of error. And this is a two-source extractor. Here we have two independent weak sources. In this case, an NK source and a DD prime source. And we want the output distribution, 2x, to be epsilon 0 close to uniform. Okay, so now we changed our graph point of view. So the edges are now not seeds, but we put an edge between two samples x and y whenever 2x xy equals 1. So a two-source extraction is a function satisfying the following. For every nk source x, for every dd prime source y independent of x, 2x xy is epsilon 0 close to uniform. And again, think of epsilon 0 as a constant or anything non-trivial. In sets notation, we want that for every x of size at least to the decay, for every y subset of 0, 1 to the d of size at least to the d prime, the subgraph induced by x and y, I'm now going to give a weaker property. We want that subgraph to be neither a clique nor an independent set. And this property, which is called a bipartite Ramsey graph, will suffice, although we do get something a bit stronger, that roughly half plus minus epsilon 0 fraction of the edges are present in the subgraph. Okay, and we focus on the less studies unbalanced setting, where n is greater than d, the left-hand side is greater than the right-hand side. And such a two-source extractor, or a Ramsey graph, is in fact a 1-bit strong disperser. Exactly the same function is a 1-bit strong disperser, where the second input is the seed of the disperser. So in terms of parameters, the error of the corresponding disperser, the fraction of bad seeds, is given by 2 to the d prime minus d, meaning the density of the sets on the right-hand side that we can handle. So the small error of our dispersers come from supporting small entropy rate rather than outputting close to uniform bit. Okay, so to summarize this part, in the two-source extractor view, there is a separation between the error epsilon coming from the bad seeds, which is this 2 to the d prime minus d, and the error epsilon 0 coming from the distance to uniformity of a good seed. Okay, so the punchline is that high error two-source extractors can imply low error strong 1-bit dispersers if they support small enough entropy. And I leave out the proof, but again, it's not a hard proof. Okay, so by constructing two-source extractors for an NK source and a DD prime source, where D prime is gamma D, what we get is a strong disperser for entropy K and seed length, which is 1/1 minus gamma, log 1 over epsilon, and an erasure list-decodable code of list size to the decay and rate, which is epsilon to the 1/1 minus gamma. So our construction must support small gammas, in particular gamma, which is less than half, in order to break the epsilon squared bound. And we indeed construct one. Great. So what's our two-source extractor? Again, given X and Y, independent weak sources, we extract one bit of the constant error epsilon 0, where K is extremely small. It's like log n. This corresponds to a smallest size of our erasure list-decodable code. And D is small, it's omega log n. And the entropy rate gamma of Y is an arbitrary constant, and this corresponds to the large rate of our code. And in this unbalanced regime of parameters, our two-source construction is close to optimal. If we do balance our parameters, we also get a balanced two-source extractor with the following parameters. The first source has entropy O of log n. The second source has entropy gamma n. And you can view this, if you know Raza's extractor, you can view this as an improvement upon Raza's extractors for the case of one output bit and constant L. Okay, so this is where our two-source extractor fits in. Okay, so two-source extractor is obviously a Ramsey graph, which implies a strong one-bit disperser. It's in fact exactly a one-bit strong disperser. And from a one-bit strong disperser, we saw how we can construct an erasure list-decodable codes. Okay, so let us conclude with just a few words about the construction. So recall that our goal is, given X, an NK source, and Y, an independent DD prime source, where D prime is gamma D, we want to extract one unbiased bit. Now, the starting point is that for entropy rate larger than half, the problem was already solved. In fact, Raza's extractor that I previously mentioned gives a construction that supports, say, gamma, which is 0.6. And in such a case, Raz applied on X and Y is very close to uniform. So from rate gamma, we want to get to rate 0.6 because then we know how to solve the problem. And how do we do that? We would like to apply an object called a condenser on Y to condense it from entropy rate gamma to entropy rate 0.6. Okay. Now we would have liked to do this deterministically and then to apply Raza's extractor, but this cannot be done. Okay, so we cannot just take our Y and condense it to some other source Y prime deterministically. So we need a seeded object, a seeded condenser that increases the density of the source. But to apply our condenser, we need a seed. So how do we do that? Of course, we could take another independent source, but we don't want to do that since we only get two sources and not three or more. So another option would be to enumerate over all possible seeds. And this would give us a table y prime. Okay, so y prime is a table of cond, our condenser, applied on all possible seeds. Now, combining existing constructions, we construct an explicit condenser having a constant number of seeds for constant error. This fact is crucial for us, okay? The fact that the table has only constant number of rows. And note that the table y prime is still only a function of y. Now, most of the rows of y prime are good. They have large density, but we prove something stronger. With high probability over y, the table y prime has many rows that are good seeds for Erasure Extractor. Recall that Erasure Extractor works for dense seeds. This way, we do not aggregate the error of the condenser. And we get, the error that we get is the error that Erasure Extractor gives us. What we can now do is apply Erasure Extractor, where X is the source, and every row of y prime is the seed. Okay, it looks something like that. Okay, so this is the construction up until now. And up until now, we have that most of the rows of y double prime are uniform, or close to uniform, and there is a small set of bad rows, okay, coming from the set of bad rows in y prime. But that's not good enough for us, because we need to output a single good value. Now, although most rows of y double prime are very close to uniform, they are highly correlated. So to break correlations, the rest of the construction uses ideas similar to the great line of works on multi-source extractors by Lee, Chattopadhyay, Cohen, Zuckerman. All those are many, many papers, not a single one. But we do need to handle some challenges that were not issued before. For example, reusing the source Y, separating errors and not aggregating them, handling a set of bad rows that depend on the samples and not only on the distributions, etc.
So I'll conclude with a couple of open problems. The first one is constructing good linear strong dispersers, meaning a function that on top of being a disperser satisfied the following linearity condition. Now this would give a good linear Erasure List-Decodable code, as we saw, and this would also allow efficient list decoding. The second problem is outputting many bits. Construct a disperser with parameters matching ours, but not a single output bit, but many output bits. And this would have applications to subspace designs and certain extractors. Okay, thanks for listening.